Welcome to the fifth online tutorial session of the NPTEL course, Physical and Electrochemical Characterization in the Chemical Engineering. So this is the online tutorial session of the NPTEL course, which has been taught by Professor Tamal Banerjee of IIT Guwahati. So I'll be handling this online tutorial. I've been handling this online tutorial session for last 4 weeks, and this is our fifth week. And we have discussed many physical characterization techniques till now. And today in this, we are majorly discussing about the measurement of surface tension and other rheological studies. So yeah, let us go further. Yeah. So I am Rahul R. I'm a pioneer research fellow at the Department of Physics at IIT Kharagpur. So as I said, for the first 4 weeks, I have been handling this session, and I'll be handling the session for the next coming weeks also. So if you have any doubts, you can come here. We will every Tuesday. The classes will be from 7 to 9. So if you have any doubts regarding this uh, NPTEL lecture, you can come here and you can ask me. So each week we will be discussing on the topics that are on that particular week by Professor Tamal, and we'll be solving some questions that are related to the lectures that are already taught. So you guys can use this for your solving the quizzes or the exams that you'll be having at the end. So this will be an extra additional classes that you can get so that you can get a firm grip on the subject. So yeah, so basically in this course, which is done by the physical and electrochemical characterization techniques, it says this is for in chemical engineering, but this, as I used to tell in every classes, these techniques are being widely used by many different branches of science, like people from physics use this, people from chemistry, biotechnology, chemical engineering, nanotechnology. All those people will regularly use these kinds of technique in their day-to-day research. So it is very important for someone who has an interest or aspiration to go for a research is coming from any of this background. In particular, if someone wants to go in research in material science or in chemistry, then there's a higher probability that they will come through all this research or these experimental techniques, and it will be very helpful for them to have a good understanding on how these things actually works. So without further ado, let's go to the class. Let's discuss our first question today. So usually our classes will be like I'll read the question for you, read out the question for you, then I'll give you a few seconds for you as to find out the answer by yourself. And then we can discuss the answer with us and discuss the answer. So it won't be a one-sided club. Here there will be participation of both students and myself. So this would be more an engaging type of class. So I believe that you guys would ask questions, would interrupt me at any point and ask me questions. Okay, so let's go. Let us start our class. Let us discuss our first question. So the first question is define surface tension. This is a very fundamental question, and this I think is the first thing that we need to understand before starting the lecture. So we have already learned this idea in our 11th. So yeah, CBSE 11X contain this question. So let us see how much you remember. So yeah, the question is define surface tension. I'll wait for a few seconds, then we will discuss the answer. Okay, I think you guys got enough time to like find your memory. So let me discuss the answer with you. So the answer is surface tension is defined as the force acting perpendicular to any image lying in a surface. For example, if you have a water, so you have a container. This is a container. Well, you're having a container and you're having water up to this level. So this is the water. Surface tension is defined as the force acting perpendicular to unit length at the surface. So what is the force that is being acted at this surface? So that particular force is called force per unit length is called surface tension. Surface tension is nothing but force per unit length. So this the surface of, for example, in this case, this surface would have just like an extended membrane. So that is a stretched membrane. Just act like so there will be a tension to that stretched membrane. Similarly, this will also act as a stretched membrane, and the value, the surface tension value, is given as the force per unit length of that time. So if there is some line like this, then what is the unit of time? And you can see, as I said, the unit of force is the unit of forces Newton, which is given as M. So the unit of surface tension is Newton per meter. So this is a very simple question. So I hope you guys were able to mm, guess the answer. So yeah, this is an easy question. Yeah, but don't be spying on this. So let's move on to the next question. Which of the following is wrong about surface tension? So there are four options that I have given you. One of them is a wrong statement. You need to identify the wrong statement. So I will read out the statements for you. The first one is surface tension is a basic characteristic of gas liquid interface. We need to the thing you need the catch is here. It's a gas. Is it a gas liquid interface? The next one is the interface resembles a thin membrane with nanometer thickness. Okay, so surface tension, in case of surface tension, the interface would resembles like a thin membrane, and the dimension of that thin membrane is nanometer. Is that the correct or is that the wrong statement? The next question is the molecule surrounding a molecule in bulk liquid exert uniform attractive forces in all directions. The other one is because the molecules in vapor phase are widely distributed, the net pull towards the liquid bulk is considerably higher. Okay, so one of the statement that I have stated here is wrong. Identify that statement. I will give the question once again. The first one is which of the following is wrong about surface tension? The first option A, surface tension is a basic characteristic of gas-liquid interface. Uh, Option B, the interface resembles a thin membrane with nanometer thickness. Option C, the molecule surrounding a molecule in a bulk liquid exert uniform attractive forces in all directions. Option D, because the molecules in the vapor phase are widely distributed, the net pull towards the liquid bulk is naturally higher. Which of the above stated statement is wrong? I can give you a few seconds for you guys to think over the answer. Then I will discuss the answer. Okay, I guess you guys had enough time to think over the answer. So the question was, which of the following statement is wrong about surface tension? Surface tension is a basic characteristic gas-liquid interface. Says the interface resembles a thin membrane with nanometer thickness. The molecule surrounding a molecule in the bulk liquid exert a uniform attractive forces in all directions. Because the molecules in the vapor phase are widely distributed, the net pull towards the liquid bulk is considerably higher. So the wrong statement in this is option B. So yeah, the option B says that the interface resembles a thin membrane with a nanometer thickness. So yeah, so we have an interface. Here it's gas. Here it's liquid. So it is said that this membrane, when we zoom in, so if we get a block, and the thickness of this block is said to be in nanometer. This is what stated in this option B. So, but the correct answer is this thickness is almost tends to zero. So actually, yeah, the interface, the thickness of the interface is almost zero. So yeah, it is taken to be zero thickness. So I hope you guys understood the answer. So yeah, the first statement is true. It is a very basic characteristic of gas liquid interface. And the second one is say is also true. You can take a bulk as well this, or you can say consider this. So here we can see that this experience equal force of attraction from neighboring molecules, all the neighboring molecules. Whereas if you consider this, just a second. Whereas if we consider this molecule or molecule, which is on the interface, so this has an attraction from this side or this side and from this side, but it is missing from the upper side. Upper side. So the pull towards here is considerably higher. So there is a force here and there is no force upwards, so there is no resultant forces towards the outside. So that is what is said in the fourth point. So that is also true. So the correct answer is option B. Correct answer in the sense the wrong statement about surface tension is that interface resembles a thin membrane with nanometer thickness. The correct answer is the interface resembles a thin membrane with zero thickness. It should be zero thickness. So I hope you guys understood the answer. Now let us move on to the next question. Define surface energy. So initially we discussed about the surface tension. Now here we are discussing about the surface energy. So yeah, kindly brush up your mind, brush up your memory. These also have you have learned in 11. So just think what is the answer, what is or define surface energy. I can give you a few seconds for you guys to think the answer. Then I will discuss the answer with you. Okay, so just think of the answer. If you have any doubt, just ask me directly. Just interrupt me at any point. I'll be right here. Okay, I think you guys got enough time to think the answer. So now let me discuss the answer with you. The surface energy is defined as to increase the area of the surface, one must transport one additional molecule from liquid bulk to its surface, which requires additional energy. This additional energy is called the surface energy. The greater the force exerted by the liquid, the greater the work accomplished. So um, basically, surface energy is work done per area. So work is given as force into distance and area basically meter square unit. So it is Newton in the meter per meter square. The answer is Newton per meter. So basically, if we have a so this is a liquid and we need to move a molecule which is somewhere down here to its surface. We have to take it to its surface. So uh, what is the energy that is required? This corresponding energy is called the surface energy. Okay, so I hope you guys understood this. Now we have to consider if we have a molecule that is deep inside the bulk of the liquid, and we need to take that molecule into the surface of the liquid. So for that we need to do some work. Okay, so this work done per unit area. Unit area is, of course, mechanical areas. Generally, we will take it as energy. So this particular uh, energy is called the surface energy, and its unit is the unit of work is Newton meter, and energy is Newton per meter square. Energy area of meter square. So the unit is Newton per meter. So in the previous slide, we were talking about surface tension. So surface tension is a basic force per uh, distance. So basically, the unit of both are same. So yeah, let's go back to the previous slide. So here we were talking about surface tension. Surface tension, it is also force per unit length, but it is the work done per unit length. Okay. So surface tension, even though there are units of same, the basic definition is different. तो इसका बेसिक surface tension is force per unit length and surface area is is work done per unit area. So it's area, so it's length, yes, force, yes, work. So yeah, this is the surface energy. I hope you guys understood this question. So yeah, let's move on to the next layer. Yeah, that's it. So derive the relation between surface tension and surface energy. Now we have discussed about surface tension, then we have defined surface energy. Then how can we relate the surface tension to the surface energy? Yeah, just try to get this answer. I will wait here for you. Just think it for a while, then I will discuss the answer with you. Okay. Yeah. What was the question? The question was to derive the relation between the surface tension and the surface energy. So yeah, I'm not going to derive it step by step. Rather, I'll give you the pathway you need to follow by deriving um, the relation, because we have already discussed that. So it is a little basic relation. So yeah, so let me discuss the answer with you. So the answer is, for deriving this, first we need to consider a rectangular frame. Okay, so rectangular frame with a movable arm. Okay, so consider, just a second. So just a second. Yeah, this is a rectangular frame, and this arm. So this is a movable arm. So this can be moved to this side or this side frame. So now let us consider there is a soft frame within this area, and the length of the movable arm is x. So this line should be taken as x, and the surface tension, the surface tension surface tension is going to be, okay. Yeah. Now consider. Now let us consider the distance it has moved to some distance b delta x. Okay. Yeah. Now the force due to this surface tension will be uh, obtained as F is equal to x. F is equal to into T into x. This is because we know surface tension is force per x. So this is, there's a force is acting on this way. So this is the unit, this is the length x. So this is the perpendicular distance. So perpendicular. So we define surface tension to be the force divided by the length, that is unit length, that is perpendicular to that force. So this is x. So from this we can write it as T is equal to x into F. I'm sorry, F is equal to x into T. Okay. So but for a film we are having two faces, one this side, the other one the back side. So that's why there is a 2 in front of this. So F is equal to 2 into x into T. So yeah, the factor 2 comes from the two surfaces of the film. Okay. Now as I said, the arm is pulled by a very small distance delta x. Then the work done is W is equal to force into displacement. So here W is this, force is into displacement is delta x. Okay. Or yeah, let me call this as dx. So it can be written as F into dx. Okay. So this is the dW of work that has been done. Now we know the area of the filling is, let me call it as dA is equal to x into dx. So this corresponds to the area of this, but this is having two faces, so we can call it 2x dx. Okay, so this is dA. Now we know the relationship, we know the equation for surface energy, that we call it as E is work done by using area. So the work done we have calculated to be F into dx. So let me some just use this is right. Yeah. So so what did we got at this point of time? Like we got d. So we got dA will be 2 into x dx. Now we know surface energy and represented by SE is equal to dW by dA. dW is nothing but F dx by 2x dx. We know F What was F? F is equal to 2 into X into T. So this is surface energy is equal to 2 into X into T into this is F into dx. This is what that divided by 2x dx. So I hope you guys can now easily do this thing. Thanks and everything which are found. That is T. So as I said earlier, the unit of surface tension and surface energy are same. Both were Newton per meter. So you can see here that surface energy is numerically equal to surface tension T. Yeah, which is nothing but the work done per unit area. This is the relation between surface tension and surface energy. Okay, I hope you guys were able to answer. So let me discuss it once again. Consider a rectangular slab with its one arm that can be moved freely to left or right. And consider the length of this arm to be x unit. Okay, so this is x units, and yeah, so initially we need to calculate the force, and let us assume the tension of this. So that then we fill a soap, what we call a soap bubble, a layer of soap into this soap film in this particular area, and so the soap bubble, when we put this freely movable hand to one side, either of the side, the soap bubble will experience some kind of a force. So consider if we are moving this away. Here I have shown this towards the, like we are compressing the bubble. Now just consider it as we are moving away towards the left side. I mean that towards the right side where you are trying to expand the bubble. So obviously the bubble would face some kind of potential energy or some kind of energy. So yeah, so the force at which we are pulling can be equal to F is equal to x T, where T is the surface tension. And if you're trying to pull, we should do some work, only then we can pull this arm away or away from this structure. Or if you are trying to move this towards right side, you need to do some particular amount of work. You can call it as dw. This dw is the work that is being done to move this movable arm for a distance dx. So once doing that, we can calculate the surface energy, which is defined as the work done per unit area. So now what is the area? So area is the area of the move area that has been moved. So that you can consider that to be a rectangle with its one side x and the other side delta x. So area of that rectangle is x delta x or x dx. Since we are having two sides for this filling, we need to consider 2a, which is 2x dx. So we have dw, which is nothing but f dx, and we have dA, which is nothing but 2x dx. Now we have already calculated f. F is equal to 2tx. So we are substituting everything in the equation. We get surface energy is equal to 2x t dot dx divided by 2x dx. By cancelling out all common terms in the numerator and denominator, we get the surface energy to be equal to surface tension. So this is the basic relationship between surface energy and surface tension. And we also need to know that the unit of surface energy and surface tension is same. It is equal to Newton per meter. Okay, I hope you guys understood this question well. I've taken enough time to explain that relation because this is a very fundamental thing and we will need to know this before going to any further. Now let us move on to next. Yeah, just a second. Okay. So the next question is, what is the formula used in the Parker method and what does it signify? So there's a particular method that we have studied to analyze the surface tension. So what is this? What is that formula which we'll be using in the Parker method, and what does it signify? Let me give you a few seconds for you guys to think over it, then we'll discuss that also with you. Yeah, I think you guys got had enough time to think over the answer. Now let me discuss the answer with you. So the answer to the relationship is given by gamma is equal to this factor Parker factor into rho L minus rho V, which is the liquid phase and vapor phase, divided by the molar mass, whole to the power 4. So this is the formula that is used in the Parker method, and it signifies that the liquid surface tension comparing their Parkers is comparable to coming the molar volumes. So this is the significance of the Parker equation. So yeah, but I'll go to the next question. Calculate the surface tension of the at electrically given the density of the 867 kilogram per meter cube. Molar mass is 92.14 gram per mole. Parker volume of C6H5 is 33.716 in 10 raised to 6 kilogram raised to 1 by 4 meter cube. Second raised to minus 1 by 3 mole inverse, and the Parker volume of CH3 is given by 9.869 into 10 to the power 6. So yeah, we need to calculate the surface tension, which is the gamma of this. Yeah, so let me give you a few seconds to calculate. So this is, so you have the formula here to itself. So you need to have a slight variation to that formula. I can give you the formula. Just try to do this. The formula is nothing but gamma is equal to rho into rho L divided by m whole to the power 4. Okay, so this is the, and yeah, just think it out a while, then I can. So this is the formula you guys need to use in this question. So I'm not going to derive all that. But once you get the formula, once you substitute it, you can do the basic calculation, and that's the answer. Okay. Okay. You guys got enough time to discuss that. Yeah, just think our answer. So let me discuss the answer. So as I said, you will be using this formula. So I've already given you a tool to solve this problem. So here we have to calculate gamma, which is a surface condition. Yeah. So it's toluene. So the formula for toluene is CH3. Formula is you have to guys know. Toluene formula is given by C6H5 CH3. Okay, so this is toluene. So now we need to, so in the class, NPTEL class, Professor Tamal has shown you a table which contains the value of Parker volume of C6H5 and CH3. So from that particular table, we can get the values to be Parker volume of C6H5 is equal to 33.716 into 10 raised to 6, and Parker volume of switch 3 can be obtained as 9.869 into 10 to 6. Now we can from this equation calculate rho to be rho of C6H5 plus rho of CH3. So this can be equal to 23.716 plus 9.869 into 10 to the power 6. Okay, so yeah, just give me that. This to the set. Yeah. Okay. So now you got this particular value and all the other values are given. So you need to calculate rho is equal to how much it is? 23.716 plus 9.869 to the power 10 raised to 6 multiplied by the rho, that is going to be 867. This is 867, and this has to be divided by how much? 92. So yeah, basically 92.14. This is gram. To convert this into kilogram, we need to multiply by -3. So this is kilogram per. So yeah, now it's just multiplication addition. So you do this and then we have the gram. So we need to remember this particular formula in order to go further, and the value is calculated by multiply. So if you're having the structure C6H5 CH3, we know the values of C6H5 and CH3. You need to add this together to get the value of rho. And we know rho, which is the density, and is the mass. So the is known to substitute, do some addition, multiplication, and then you get the answer. So this 4 power 4. This has to be the power 4. So I hope you guys can do further. So this is the answer to the question. Okay. Now let me go to the next question. Calculate the density of acetic acid at 298 Kelvin. So you need to think, you need to be aware that I'm specifying the temperature also. So all these calculations are dependent on temperature. So you calculate a number that. And the surface tension of acetic acid, you need to calculate density. We notice, so the previous question was to calculate the surface tension. Here the question is to calculate the density. So here given, it is given that the surface tension of the acetic acid is 0.027 Newton per meter. Molar mass is 60.052 gram per mole. Paracca volume is of CH3 is 9.869 and the 10 to the power 6, and COOH is 13.124 into 10 power 6. The value is 2.125 and meter cube. Second in raised to -1/3 and 1 into. So yeah, just try to calculate this. We can use the same formula. and you can use that formula to calculate the answer also. So just try to calculate the answer. I will tell you the answer right within a few seconds. Just try to do it yourself, and if you have any doubt, just ask me. Yeah, I guess you guys had enough time to think about the answer. So let me now discuss the answer with you. So, so as I said, we can use the same formula here also. So the formula we used was some percentage gamma is calculated by the wave in the area divided by m or to the power of 4. So in this question, we are asked to calculate the surface density of acetic acid. We need to calculate not surface density, I'm sorry. We need to calculate the density of acetic acid, which is nothing but rho. So we need to replace this equation. So this is nothing but gamma power 1 by 4 times m here in the real can be equal to 4. This is a modified equation that we need to use for solving this particular problem. So here the value of gamma is given as 0.027 and Newton per meter, and the value of m is given as 16.052 gram per mole, and you can calculate for it. It is given it is given. So yeah, for this we need to know what is the chemical formula of acetic acid. It is nothing but CH3COOH. So it can be split into CH3 and COOH. Okay, so from the data that has been provided by Tamal in this lecture, we can get the value of CH3, about value of CH3 to be 9.869 into 10 to the power 6. And yeah, there's a whole bunch of elements associated with it. And let me not write those things. And where associated with COOH is 15.124 into 10 to the power 6. So now we can calculate the volume to be 9.869 plus 13.124 to 10 to the power 6. So from these informations, you can calculate rho, which is the density of acetic acid, to be 0.027 to the power 1 by 4 multiplied by molar mass, which is nothing but 16.052. It is in gram per mole, and this is gram per mole, and divided by the mole, which is nothing but 9.869 plus 13.184 for 100 to 6. This is kilogram just meter. Sorry, this become the value of flow for acetic acid. So I hope this is clear to you. This is the basic principle. So this is a very basic equation that one has to know for all these kinds of calculation. And just remember, this is given in a particular temperature. This means that all these calculations are temperature dependent. Okay. Yeah. If everything is okay, let us move to the next question, which is the water drop of 5 millimeter radius is split into 50 tiny drops. Find the increase in the value of surface energy. So how much does the surface energy actually increase? Okay, so there is a water drop and the size of the water drop is 5 millimeter. Now this 5 millimeter water droplet is split into 50 tiny drops. So now what is the increase in the surface energy? So yeah, let me give you a few seconds for you guys to think about the answer, then I'll give the answer. Got enough time to think about answers, so let me discuss the answer with you. Yeah. So the surface energy of a water drop is proportional to its surface area. So we know that surface energy is proportional to surface area, in which in turn proportional square of its radius. Yeah, proportional square of its radius. Now the surface tension T and the radius of the original drop, let it be R. Then the surface energy is E is proportional to. So you know E is proportional to how much? T times R square. So there is some constant 4 pi. So basically the area is given by 4 pi R square multiplied by T. So surface energy proportional to this. So we know this. Now, if the original drop is split into 50 tiny drops, then the radius of each tiny drop be R. The volume of the original drop is equal to volume of tiny drops. Yeah. So we know, like there initially there was a volume. So just say there is a volume V. Now it has been divided into 50 So there are 50 droplets here. So, but still the volume would remain same. So we can write here as 4 by 3 pi r cube is equal to 50 times 4 by 3 by r cube. Okay, so I think you guys understood how to do this. Okay, so solving this, so here we can cancel out this, and yeah, we can calculate here r is equal to r by 3.68. Okay, so how do we get this? We know 4 by 3. So from this we cancel out this everything. R cube is equal to 50 r cube. So r cube is equal to r by 50 r cube by 50. So r is nothing but r by 50 to the power 0.333 or just 1 by 3. Doing this, we can get the value to be 3.68. Now, we can get the surface energy for each tiny drop is E. Now, we are having 50 tiny drops. The surface, the corresponding tiny surface energy for this be E, small letter E, and that is given by 4 pi r small r square into T. So this is nothing but 4 pi T small r can be written as r by 3.68 the whole square. So total surface area of 50 drop can be 50 E. So let me write this. We know small letter E, which is the surface energy of a smaller sphere, uh, water drop, and its corresponding surface energy can be derived for pi small r square with T. We have calculated small r to be r by 0.3. How much was it? Say not 3.68 whole square into T. So there are 50 such, so total heat of 50 such particles is E prime. So that is 50 times E. So this is the 50. So I hope you guys understood this. Now we can calculate the delta E, which is nothing but E prime, which is the new state of 50 molecule for minus the initial. So if we calculate all this, we can calculate it to be So this is nothing but 4 pi r square T into 50 divided by uh, 3.68 the whole square. Okay. So yeah, by cancelling out everything, we can calculate it. So initially, see this term. This term is nothing but our E. 4 pi r square to r square. So E prime can be done as E into 50 divided by 3.68 the whole square. So this can be simplified as E prime is equal to 0.74. Now doing the calculation, delta E is equal to 0.748 minus E, that is equal to minus 26 T. So this implies that the delta E, that is the energy difference between the new state, which is 50 tiny droplets, which has a difference from the original state, which was a whole 5 millimeter radius water drop, is minus 26 E. So there is a difference of this. Basically, converting this into percentage. So this is just a change. So I can write it as that this is the E is equal to E minus E, right? So this is also totally fine. So this is 0.26 E. So this is what we get. In terms of we can calculate delta E into right. So this is the change percentage. This is 26%. So thus we got the answer. So the change, so surface energy is decreased by 26%, like which is equal to 50 tiny droplets. Okay, now let us go to the next question. The surface tension of a majority of liquid dash as the attraction forces between the liquid molecules. surface tension of majority of liquids that has the attraction for between the liquid diminishes. So yeah, what is the thing of a majority of liquids? So what happens to surface tension as the force between the liquid molecules diminishes? So we'll just leave it for a while, then we'll discuss the next one. So we are already halfway through, so let me just move through the procedure a little bit faster so that we can handle the whole material that I'm. Yeah, I think you guys have enough time to think the answer. So surface tension of majority of the answer is actually it decreases. So the surface tension of majority of liquids decreases as the attraction field between the liquid molecules diminishes. So this is a very good concept that one is going for one to know. The answer is actually it decreases. Okay, so I will hope you understood this one. Now let us move on to the next question. The Edwards-Ramsey shared equation correlates dash and dash. The Ramsey-Shields equation correlates dash and dash. Okay, so this equation actually correlates between some of the things that we have already discussed. So this is a very fundamental equation, and this has a very crucial importance when we are actually discussing something physical, practically. So Otto's Ramsey shear equation actually correlates dash and dash. What are the two parameters that this equation correlates? So let me give you a example. So dash three. So let me discuss the answer. And you guys not enough time to think about the answer. So outpost Ramsey Shields equation actually correlates between the surface tension and the temperature. So it actually correlates surface tension and temperature. Okay, so this is very crucial because we all know that surface tension is dependent on temperature, but how does that dependence actually is? So this is equation actually tells us how the surface tension correlates with the temperature. Now let me go to the next question. Write the Electrochemical equation and explain its parameter. So yeah, so you need to write the equation and you need to explain what are those parameters. So let me give you a few seconds. Just think over the answer. Then we discuss the answer. So now let me discuss the answer too. So yeah, the Otto-Ramsey Shields equation is nothing but this, which is surface tension as a function of molar volume of the liquid to the power T by 3 is equal to some constant Ke times Tc, which is effective to critical temperature, and T is the measurable temperature minus 6. So yeah, Ke is a constant for non-associated liquids, and the value is taken to be 2.12, and for associated liquids, the value is taken to be less than 2.12. So the question is gamma as a function of liquid to the power 2 by 3. So this is the molar volume of the liquid is equal to some constant Ke times some critical temperature PC minus T minus 6. So this is the equation. Now let me move to the next question. Write the Brockberg's correlation and experiments parameter. Okay, so what is this Brockberg correlation, and write it and explain its parameter. Okay, let me give you a few seconds for you guys to think of the answer, then I'll discuss the answer with you. Okay, yeah. Sorry. The answers. So, yeah, just do it for a while, then I'll discuss the answer with you. I think you guys got enough time to think about stuff, so let me discuss the answer with you. So the answer to this question is, just a second. Let me go back to the slide. Yeah. The Brockbird's bird code correctly establish a correlation between surface tension. Just a second. Turn on my then yeah. It actually correlates between the surface tension of a liquid and liquid's critical properties in the points of the surface tension is given by Tc to the power 2 by 3 Tc to the power 1 by 3 Q times 1 minus Tr into 11 by 9. So here Q is given by another one of the big formula, which is this. Here Tb is a normal boiling point of the liquid, Tc is the critical pressure, Tr is the reduced temperature. The quantity this um, is basically is a dimensionless quantity, and K is the Boltzmann constant. So this is the Brockberg correlation, and yeah, so this is it. Now let me move on to the next question. So what are the major surface tension measurement techniques? So what are the major techniques that are used to measure surface tension? Think it for a while, then I will let you know the answer. I think you guys were ready to push this answer. So the answer to this question is drop weight method, denoising method, and Levy weight method. Okay, so the three major techniques that I use are drop weight method, denoising method, and delayed weight method. So I guess we can move on to the next question, which is what is the principle behind drop weight method? Yeah, what is that principle which which drives this drop weight method? Just think it for a while, then I will give you the answer. Discuss the answer. So yeah, the basic principle is that as the size of the drop at the tube tip increases, its weight goes up. Yeah, obviously, we all know as the size of the drop increases, its weight increases. And the drop stays attached to the tube owing to the upward for acting on the surface tension across the tube dimensions, tube's diameter. Now consider we have a tube and there is this opening. So as the and there is this drop that is actually coming down. So as the size of this drop size increases, its mass also increases. Trivial. Now this is staying here due to the surface tension of this liquid. Now when it is being pulled down by its weight mg, which is due to the gravitational force. So the surface tension is balanced by the gravitation. I mean, the gravitational force is balanced by the surface tension. So this, so at a point when the mg becomes greater than t, the drop actually falls down. Okay, so this is the basic principle behind drop weight method. Okay, so what we do here, so consider we are having a drop that is actually coming from this very small radius, so diameter, so diameter and the corresponding radius is r. Okay, so when the size of this drop actually increases, the mass also increases, and thus the gravitational pull towards downside will also increases. So when this downward pull, which is mg, becomes greater than the surface tension T, this drop actually breaks off from this T and then gradually falls down. So yeah, so this is the basic principle that is behind the drop weight method. So I hope you guys understood this one. Now let me go to the next question, which is what is Tate's law? You guys got enough time to discuss the thing about answer. Now we will discuss answer. The Tate's law actually relates the mass of a liquid rock with surface tension, radius, and gravity. It is used in the stalgometric method, a technique that is used to measure the surface tension by counting the number of drops that actually falls from a capillary tube. This is given by m is equal to 2 pi r naught gamma by g, where m is the mass of the drop, r is the radius of the tube, the actual rho is the surface tension, and g the gravitational acceleration. So here R naught is the radius of the tube, which is the radius of the tube. Okay, so Tate's law, which is given by m is equal to pi r naught gamma by solution. So this is nothing but, let me explain you how we do it. So we know from the last that relation also D can be equated to the surface in tension. So which is here we are getting a percentage energy. So yeah, we are getting 2 pi r naught. Yeah, it is about percent distribution in this manner. So here we can calculate G. We can calculate M as the 2 pi r naught gamma by G. So this is the Tate's law. Now let us go to the next question. What is the material used in a tensiometer in Donaring method? So in Donaring method, we generally use a tensiometer. What is generally the material that is used in a tensiometer? So let me give you a few seconds for you guys to think about the answer, then we will discuss the answer with you. Okay, now let me discuss answer with you. So generally, the material that is used in the tensiometer is nothing but platinum iridium alloy because its geometry doesn't change. So in Dolnar method, the geometry of the material, the ring balance that is used is very important. So generally, in order to preserve that geometry, we use platinum iridium alloy, which generally doesn't change shape or it doesn't both and then with the information. So that is a very degrees. That's why you are using this platinum will keep a lot in the tensiometers, which is basically means donor with method. What should be the speed at which the ring should be lower in a donoring method? So what is that speed of the ring? Should at what speed the ring should be lower in a donoring method? So if you give me a second for you guys to think of the answer, in order to do the answer. Okay. So yeah, speed generally at which it is used is the it is basically this generally and for the second. So this is the individual speed of which we prove that we will overall the ring in the Nare method. That's answer. Now let us go to the next question. What are the precautions that must be followed by the and ionic Nare method? What are the basic precautions that one need to follow while doing it demonic method? So that the various second for you guys to do the answer. Discuss that. You guys got enough time to think out the answer. So yeah, let me discuss the answer with you. So answer is a major precaution that one needs to be taken care is that the platinum iridium ring should be cleaned in the Bunsen burner to achieve contact angle to be zero. The ring that is used is very fragile and it is prone to deformation. So this should be prevented by putting it in a very smooth surface. The surfactant solution, it must be properly washed with pure water to avoid surfactant particles causing measurement errors. So when used in viscous oils such as silicon oils or crude petroleum, make sure that a thorough cleaning with suitable solvents such as acetone is done to remove any remaining oil. So the first one is to make sure that the platinum iridium ring uh, is cleaned by burning it in a Bunsen burner to achieve contact angle to be zero. Then the ring is a very fragile and it is very much prone to deformation. So it should be prevented by putting it in a very smooth surface. While using surfactants, it should be washed uh, properly with pure water to avoid surface particles causing any measurement errors. But while using the viscous oil such as silicon oil and the crude petroleum, we need to ensure that it should be clear and it should be cleaned very much using some solvent as acetone to remove any remaining oils. Okay, now let us go to the next question, which is how does the surface tension defined in the mm, Will Willemly plate technique? Willemly plate technique. Okay, so how does the surface tension defined in Willemly plate technique? So think it for a while, and I will discuss the answer now. Yeah. And so the surface tension in Willemly plate technique is defined as gamma is equal to F by T cos theta. So in Willemly plate technique, the surface tension is defined as F by P cos theta. So P is plate's weighted perimeter and theta is the contact angle. Okay, so I hope you guys understood the question. In Willemly plate technique, this tension is defined as gamma is F by T cos theta. Where P is the plate's weighted parameter and theta is the contact angle. So let me move on to the next question. What are the advantages of Willemly plate technique? Yeah. What are the advantages of Willemly plate technique? Willemly plate technique. Okay, think it for a while, then I discuss them. Okay, now let me discuss the answer with you. The Wilhelmine plate technique is a method for measuring the surface tension or interfacial tension by using a thin plate that is partially immersed in a liquid. The major advantage of this is that no correction is required to measure values obtained by this method. So usually in many other definitions we use a correction parameter and we don't need such kind of parameter in this. Then the next advantage is the density of the liquids don't have to be known. So we doesn't need to know any information about the density of the liquid that has been measured. For them, it is not just like the other methods. So in previous method, we need to have an idea about the uh, densities of the liquid that are being measured. And the last point is the phases don't become mixed as the plate is only touched and not moved. So here the two phases, like the two liquids that are being separated, doesn't need to be mixed because here we are not actually moving the plate. We are just it's just touched. We are not just moving anything. So it means that the two liquids that doesn't become mixed to one another. So that are the major advantages of Windy plate technique. Now we go to the next question, which is compare Doran method with the Windy plate technique. So think it for a while, then I'll let you know the answer. Okay, now let me discuss the answer with you. The major comparison between these two techniques are preliminary techniques that are majorly used for measuring the surface tension or interfacial tension of the liquids by using a very thin object that is partially immersed in the liquid. Okay, some differences between them are the major difference are Lamely plate is a stationary while donor ring method is pulled through the surface to make the measurement. The Lamely plate it requires complete weighting of the plate, while in the donor ring it requires a correction factor to occur for the contact angle of the ring. The Lamely plate can only measure the surface tension of the liquid air bubble, while the donor method can measure more surface tension and superficial tension at the liquid interfaces. So these are the major comparison between donor method and Lamely plate technique. The next question is a glass plate of width 2 centimeter and thickness 0.1 millimeter is used to measure the surface tension of water at 20 degrees Celsius. The plate is attached to microbarrels and immersed vertically in water. The force of the plate is measured to be 0.0736 millinewton. Assuming complete weighting of the plate, calculate the surface tension of the water. So we need to calculate the surface tension of the water. It is given. The width of the plate is given. The thickness of the plate is given, and the temperature at which the motion should be made is given, and the that is being acted on the plate is also given, which is 0.0736 millinewton. Now try to solve this, and we need to get the surface tension gamma. So what is the surface tension of the material or the liquid that is being used? So think it for a while, then I will discuss the answer with you. So we are nearly ending the session, so let me discuss the answer with you. So gamma can be calculated by using the formula. Yeah, we know F can be calculated using the gamma P cos theta. Then the gamma can be calculated by F by P cos theta. Here it is said that there is conflict within, so cos theta can be taken to be 1. And yeah, and we know F is given as, so what is the F is given as 0.0736 millinewton, and we can calculate P, which is nothing but here we are having two sides, so we need to calculate 2 times W width plus thickness, so that is 2 times width is 2 centimeter, 2 centimeter plus 0.1 millimeter. So this together we can get 4.02 centimeter. Now finally calculating gamma, we can write it as 0.0736 into 10 raised to minus 3 Newton divided by 4.02 into 10 raised to minus 2 Newton. So this is nothing but gamma is equal to 0.0736 into 10 raised to minus 1 divided by 4.02. That much Newton per meter. Solving this, we can get the value to be 0.0183 Newton per meter. So the formula that one must use is F is equal to gamma P cos theta. Okay, I hope you were able to solve this question. Now let us move to the next. What are the different phases in the maximum bubble pressure method? Let us not waste the time. So answer to this question is the difference of the phase one is the bubble is a small and spherical. The pressure inside the bubble is equal to the atmospheric pressure plus the hydrostatic pressure of the liquid product. Then the phase two is that bubble grows and it elongates and the pressure inside the bubble increases as the gas flow rate increases. The pressure reaches a maximum when the bubble radius is equal to the capillary radius. And last phase is the bubble detached from the capillary and rises to the surface. And the pressure inside the bubble decreases as the gas flow rate decreases. The maximum pressure is in the phase two is used to calculate the surface tension of the liquid using the Laplace equation. However, this thing is clear. And let us go to the next question. What is the common difference between Grifalco good correlation and Fox correlation? So let us not waste the time. Let me discuss the answer. The major difference between the Grifalco good correlation and the Fox correlation is that the former consider the interaction between two phases to be proportional to geometric mean of the surface energies, while the later consider the interaction to be proportional to geometric mean of the dispersion components. The Fock correlation assumes that non-dispersion forces such as polar or metallic forces are negligible and dependent. In the Fox correlation is a special case of Grifalco group correlation, and it can be derived by setting the interacting parameter to be equal to 0 to the dispersion component of the surface energy. So this is a basic. So basically, this Fock Fock correlation is a special case of this Grifalco group correlation. So that is the basic underlying difference between these two. Okay, so let's go to the next one. So this is a match the following. Revealing the questions. So it's superhydrophilic, hydrophobic, superhydrophobic, and how it is related with the contact angle. For which one the contact angle is less than 90 degrees, for which is greater than 90 degree, for which the contact angle is 0, for which the contact angle is 90 degree, 150 degree. So let me discuss the answer with the for hydrophilic, superhydrophilic, the contact angle is actually 0. So hydrophilic it is less than 90. So for hydrophobic, it is between 90 and 150, and for super hydrophobic, it is greater than 150. So I hope this is clear to you. Let me go to the next question. with the equation. That is here the equation. So let me not waste the time. So we have put the equation say that relates the contact angle of a liquid on a solid surface to the surface tension of the liquid and the interfacial energies between the liquid, the solid, and the air. It is given by gamma, which is the surface tension of air and solid to the liquid solid to the air liquid, and this is the contact angle theta. So when the surface tension of um, air solid is greater than liquid solid, then the contact angle is less than 90 degree. And if the uh, air solid is less than surface tension of the air solid is less than that of the liquid solid, then the uh, this is hydrophobic. So let us go to the next question. Calculate the work of addition. The surface tension or the contact angle of the liquid on the solid surface if the surface tension of the water is 72 millinewton per liter and the contact angle of the water is 0. So here, given that surface tension is given and the contact angle is given, we need to calculate the work of addition. Okay. So let me not waste the time. So the formula we need to use is the gamma LV 1 plus cos theta. Here the gamma value of gamma LV is given as 72.8 into 10 raised to minus 3 Newton per meter. The 1 plus cos theta is going to be 0 degree. So this is nothing but 72.8 into 10 raised to minus 3 Newton per meter into 1 plus 1. So that is nothing but 72.8 into 2 into 10 to the power minus 3 Newton per meter. That is how much? 6, 5, 14, 14.6 into 10 to the power minus 3 Newton per meter. So this is the answer. That is given by 145.6 millimeter per meter. So I hope this is very clear to you. This is the formula we need to use. Let us go to the next question. What is Young-Laplace equation and what is the significance of it? So the Young-Laplace equation is a formula that describes the pressure difference between two static fluids such as air and water across the curved surface of a thin wall due to the phenomenon of surface tension. It is given by delta P is nothing but gamma times 1 plus R1 plus 1 by R1 plus 1 by R2. But delta P is a pressure difference, gamma is the surface tension, R1 and R2 are the principal radii of the convection of the water. The major significance of it is that it allows us to understand the shape and curvature of the surface or the wall affect the pressure difference between the two fluids in contact with it and vice versa. This is important. This has important implications for many phenomena involving surface tension such as capillary action, bubble formation, droplet spreading, wetting and deviating, etc. And basically, this can explain the soap bubble, why the soap bubble has higher pressure inside than outside. And it can also explain why the liquid droplet on a solid surface can have contact angle depending on the surface energy and surface tension of the liquid. I hope this is clear. Now let me go to the next question. The soap bubble has a radius of 2 centimeters and a surface tension of 0.03 Newton per meter. What is the pressure difference between inside and outside of the bubble? So think this for a while, then let me discuss that. So we have discussed the formula in here itself. So yeah, the formula was nothing but delta 3 is equal to gamma into 1 by R1 plus 1 by R2. Okay. Yeah. Let's see how much we can go further. Okay. Here, since we are considering a bubble, let us consider the radius, the thickness is very small. So let us consider the R1 and R2 equal to 0.2 centimeter. That is nothing but 0.02 meter. So and the gamma is given like this. So the already now the answer is very simple. 0.03 into 1 by 0.02 plus 1 by 0.04. Okay, this is nothing but 0.03 to 1 by 2 to conversion minus 2 plus 1 by 2 split. So this is nothing but 0.03 divided by 100 by 2 plus 100 by 2. So this is nothing but 0.03 to 50 plus 50. That is 0.03. So this is 3. The pressure. This is like mistake over here. This is like mistake over here. Just one second. So, yeah. So the answer to this question is here actually should be 50. Should be 50. So the answer is that V is equal to 3 into square. So that's it. So yeah, let me try substitute this characteristic. So delta T is nothing but 0.3 into 1 by 0.02 plus 1 by 0.02. 0.02 can be written as 1 by 2 into 10 to the 1 minus 2. Yeah, minus 2. And yeah. Yeah, it's been 26. Yeah, so the answer. So the pressure difference delta T is equal to there is a nice space 3 Newton per meter square. Okay. Okay, fine. Now let's move forward. Let's move forward. What is Kelvin's equation? So basically, Kelvin's equation is an equation that describes the changing vapor pressure due to curved liquid vapor interface, such as surface of a droplet. So this is can be found using this formula V2 by P the exponential to n gamma by RT rho L. So yeah, this is it. Now let's go to the next question. The capillary radius of the capillary tip of radius 0.2 millimeter is deep vertically in the water. The surface tension of the water is 0.072 Newton per meter, and the density of the water is 100 kilogram per meter cube. The angle of contact between water and glass is 0. What is the height of the water column? That column in the capillary tip. For this, we need a formula. The formula is nothing but height h. We need to calculate the height h. It's nothing but 2t cos theta divided by R rho G. Okay, so all the parameters are given. 2, t is given. How much is the surface tension? 0.072. The cos theta is cos 0 degree divided by R is given as 2 millimeters. That is 3 into 10 to the power minus 3 meter into rho is given as 1000 kilogram per meter cube. And G, we know it's 9, we'll just take it as 10 and meter per second square. So it is nothing but 2 into 0.72, 0.072 divided by 2 to 10. So you can calculate, you cancel these two out. The answer is 0.0072 meter. So this is actually, this can be written as 0.72 millimeter. So answer is approximately 0.72 millimeter. I mean 7.2 millimeters, not 0.72. 7.2. Yeah, 7.2 millimeter. Okay. So yeah, approximately. Yeah, probably actually 70 centimeter. So well, that's the answer is approximately 7.5 centimeter. So I hope you got the answer. The major trick is to use this particular formula. Okay, now let us go to the next question. Derive Laplace equation from capillary radius equation. So I can define the step. So these are the steps. Assume the cylindrical capillary tube with radius R and the liquid column of height h inside it. The liquid air interface form a meniscus with the contact angle theta at the wall of the tube. Now, by applying the hydrostatic equation to the liquid column and the above, we can make sure that the pressure difference between the liquid and the air at the same height is given. Delta P is equal to rho GH, where rho is the density of the liquid and G is the acceleration due to gravity. Now, by applying Young Laplace equation to the meniscus and related to pressure difference to the curvature of the interface, we can calculate 1 by r is equal to 1 by r cos theta, for capital R is the radius of the meniscus. Now, substituting for delta p and 1 by r in the Young Laplace equation, and simplifying it, we can get the capital rise to be h is equal to t rho r T by r rho g cos theta, where t is the surface tension of the liquid. So this is a very similar exercise that has been done by Professor Tamal in the class. Already we go to the next question. What is a bond number? So basically, bond number is a dimensionless number that measures the ratio of gravitational forces to the surface. So it is basically the ratio of gravitational force to the surface tension force of a liquid bond. So basically, it is given that V0 is equal to rho r g a square by t, where rho is the density of liquid, g is the acceleration due to gravity, r is the radius of the drop, and t is the surface tension of the liquid. So now just try this question. A water drop of radius 2 millimeters placed on horizontal surface. The surface tension of the water is 20 degrees Celsius. At 20 degrees Celsius is 0.0728 Newton per meter, and the density of water is 1000 kilogram per meter. What calculate the bond number of the drop and common damage shape? So yeah, we know that bond order B0 can be calculated by using the formula rho G R A square divided by T. So this is the formula we can use. So here we know all the parameters we can calculate. Rho is given as 1000, G can be taken as 10, and RA is 2 into 10 raised to minus 3 meters. So this much meters divided by T is given as 0.0728 meter per meter. So yeah, cancelling out this and simplifying this, we get the value to be 0.054. So here we have taken the so this is for by taking the G to be 9.81 meter per second square. So by calculating this, we get the value of, so this is basically a ratio. So here we don't have any units, so this is 0.44. So here the bond number is very small, which means that the gravitational force is negligible compared to the surface tension. So therefore, relatively in this verification. Okay, now let's move on to the next question. A drop of oil of density 800 kilogram per meter cube and radius 0.5 millimeters suspended on a water with density 1000 kilogram per meter cube in a cylindrical tube of radius 2 millimeters. The tube is rotated at a speed of 3000 rpm. Calculate the interfacial tension between oil and water using spinning drop method. So yeah, I think this is our last question. So here we need to calculate the surface tension by using the formula T is equal to rho2 minus rho1 to omega to the power 2r 4 by a L square. So by using this formula and substituting all the values, here omega should be calculated by the formula 3000 into 2 pi by 60. So here we are getting it is RPM. So converting RPM to omega, we are using this formula and every other values is given and substituting into this formula. So here there is the water, which is the 1000, and now the is given, which is 800. So substituting everything, omega we got in this way, and R is small letter r is given as 0.5 millimeter. So it should be 0.5 meter 10 to the power minus 3 meter, and substituting everything. Yeah, it's actually 2 millimeter, it's 3. So yeah, so calculating everything, we get the answer to be 0.002 meter per meter. So yeah, I think this is it. So if you guys have any question, you can directly ask me on the next class, or if you have any other questions also regarding the previous class, please do ask to me. These videos will be uploaded on my YouTube channel, and the link will be shared to you by the NPTEL team. So if you have any further doubts, please do clarify it on the very next class. Thank you. I hope everything is clear. We'll see you on the next video.